Okay, guys, let's talk about partial derivatives. I want to share my slides with you now. And here's a definition of what a partial derivative is, what should be on the screen now. So let me talk about what I have on the screen. A partial derivative of a multivariate function is just the rate of change with respect to one variable, in other words, the derivative with respect to a variable, while holding all of the other variables constant. And I'm not even saying how many variables there are in this function. It's true, no matter what. If there's 10 variables, you can take the partial derivative with respect to one of the variables, and the other 9, you treat them as constants. So my next bullet point there is an example where there's just 2 variables. Z is a function of x and y. That's how you might read this. Z equals f of x and y. The comma becomes an and, right? Z is a function of x and y, or z equals f of x and y. Then you can say this curly d, it's like dz dx. In fact, it is still a d. It has this just weird script added to it. And this is the convention when you're taking a partial derivative instead of just a standard total derivative, is to have the d be curly here. I usually read it, instead of saying curly d, I say something like the partial of z with respect to x, something like that is what I would say. Even though it is just a curly dz over curly dx. Someone's here, add them. Okay, so what is partial of z with respect to x? It's the derivative with respect to x of this function holding y constant. Simple. We've already done stuff like that with parameters, right, and exogenous variables. Well, now it's just a little more formal. Maybe x and y are both endogenous variables, but when you're taking a partial derivative, you treat only the one that's in the denominator here as the true changing variable, and the other one is just constant. So partial of z with respect to x, or the partial of z with respect to y, those are 2 different things. The only difference is which variable is changing and which one is constant. So you actually, this function z, or sorry, I guess f is the function. This function f has 2 partial derivatives, one for x and one for y. I also wish I had written here, I still can, I'm going to annotate this, to say, here's another way you might see this written. I'll write it over here. F with a little subscript x. I will use this notation in the class. When you see f with the little subscript x here, and it's already been made clear that f is a function of 2 variables x and y, or multiple variables x and y. If this has been established, z equals f of x and y, then you can write this here, f with the subscript x, and that means the same thing, the partial derivative of f with respect to x. And same thing, this one down here would be f with the little y. I'm going to say that later, I'm sure. Okay, so, and also, what if there's more than 2 variables? There could be however many you want, all the way up to n. You can still talk about the partial derivative with respect to each of those variables. And like I said before, what you do is just hold all of the other variables constant. But you use the same rules of differentiation. You already know the rules of differentiation. So this is not any harder than what we've already done. Okay. Let's do some examples now. You guys want to try these? I'm asking you to find dz dx and dz dy, where those are both partials. Maybe I'll do annotate. Should I write on my pencil and paper, or should I annotate it right here on the screen? What do you guys think? You care?
I don't have a preference.
Okay. Well, first, let's write. I'll do paper and pencil now since I have. And let's see how lousy that is. That means spotlight this video. Okay. Now what you can't see is what those were. The first one was z equals x squared plus 3y squared. Okay. I sometimes like this little line there in my z, so you can tell it's a z, not a 2. How would I find this? The partial derivative of z with respect to x? Someone just tell me the answer.
Is it 2x?
Yep, it is just 2x. That whole 3y squared, just ignore that. Good. And the partial with z with respect to y. Six y, right? It's really simple here because for this one, the y is treated as a constant. It goes away. It just becomes 2x. Same thing here. Let's get a little bit harder one. 4xy cubed. Then what's dz dx? Can somebody else tell me what this one is here, dz dx?
Is it just 12x squared?
Good guess.
Um,
Nope. The key here is to treat that y cubed as a constant. 4 is a constant. The only variable there is x. So it's almost like, it's linear with respect to x. What would dz dx be?
Would it be 4y cubed?
That's correct. Why is it 4y cubed? Because, if it were 8x, you would know, okay, the derivative is 8. If it were 100x, you would know, oh, the derivative is 100. If it were 4y cubed times x, you should know the derivative is 4y cubed. It's simply the coefficient that's being multiplied by x. So when you take the derivative, what you get is 4y cubed. And this is the first time you really kind of see what's happening with partial differentiation. You're getting something about what's happening with x, and you're just sort of leaving y alone. The y cubed is there; it's still there. Here there was a y squared here that disappeared, and you might say, well, why did the y squared disappear here, but it stays here? And it's important. It's because this was being added, and this is being multiplied. And of course, if you have a real life function where things are being multiplied to each other, there's a lot more effect of x on y. These two variables, x and y, they'll affect each other a lot more. What I said when I say affect each other is they work together to have an effect on the outcome of the function a lot more when they're multiplied to each other than when they're simply added together. So that's why this one has a y in it and this one doesn't. Okay, let's continue on. What's dz dy here?
12xy cubed or squared, sorry.
12xy squared. Does everyone agree with that? I agree. And I'm the instructor, so it's got to be right, right? No, I'm sometimes make mistakes, but I think in this case, yeah, he's right. Who said that? I'm sorry, I can't tell who's talking. Sometimes it pops up and other times it doesn't. Are we just never going to know who that was? A mystery voice answered correctly that it was 12 xy squared. This is what we're doing right now. We're doing partial differentiation. What I'd like for you guys to be able to do is to take the partial derivatives of any function. I give you a function, you tell me not just one, but all of the partial derivatives of that function, right? If it's got two variables, then there's going to be two partial derivatives. It's got 3 variables. They're going to be 3 partial derivatives. But you could just do it. You could give me each one. And that tells me something about how this function changes. Let's not forget that's what the interpretation of this is. What is the interpretation of this curly dz over curly dx equals 2x? That means if I were to increase x by 1, this value of z would increase by whatever 2 times x is. So if x is currently 10, and I want to increase it from x equals 10 to x equals 11, really we should be thinking instantaneously changing it. So rather than a discrete change from 10 to 11, but just sort of the instantaneous increase in x. If x were already 10, then this says something about the rate of change of z with respect to x. It's 2 times 10. It would be roughly 20. That's what that means. It means the same thing here. Like if I say, well, x is 10 and y is 2, and I'm thinking, okay, well, how does increasing x affect z? Your answer actually depends on y. Because how the larger y is, the more effect increasing x will have on z. This is me saying a lot of words that refer to numerical values, which maybe you're the type of person who would rather see a visual of that. Like, well, you're talking about all this stuff. Why can't you just graph it in terms of slopes and things like that? Well, it is pretty hard when you're talking about this 3-dimensional stuff. I think I addressed this last class that already when you have 2 inputs into your function, you're talking about a 3-dimensional graph. And of course you can draw it, you can try to draw it and try to approximate it, but it's actually not very satisfying. I would rather you not rely on a visual interpretation of this function to get to like figure out what's going on here, or at least have some feeling for, okay, I think I understand what's happening. Really just think of the math involved, that this dz dx is saying the rate of change of z with respect to x is equal to 4 times whatever the value of y happens to be cubed. Right? If y happens to be 0, then changing x has no effect on z if y is 0. That's true, because then the function is always 0. Z will always be 0 if y is 0. So changing x doesn't change anything. Anything times 0 is 0. Does that make sense? So it's just sort of this. It's a little. The intuition may be different than what you're used to, because in a function like this, what's going on the margin with x is determined by the actual value of y. It's like flipped. Okay. In here, though, this case is a little different because it actually matters both what x and y are. If you want to know what's the rate of change of z if you were to allow y to change, the answer is, well, 12 times x times y squared. You have to tell me what x and y both are before you could get some answer to that question. Another way to say this is linear in x. Z is linear in x, isn't it? That's why its derivative doesn't have an x in it. Okay, let's go on to some other examples, because after all, these were just 2 examples. Y times e to the xy. Let's do that one. Here's a shorthand, dx. I'm already using my shorthand here with the little subscripts. That means don't do that for regular derivatives. Only do it for partial derivatives. You know what the shorthand for regular derivatives is? A prime. You put a little prime there. That means that's what we mean when you think of the derivative of a function with just one variable. You don't have to write a subscript. In fact, it would look weird if you did. You would just write like z prime, for example. You could do that if there was only one variable that was the input. When there's 2 variables as the inputs of the function z, then you need to use the subscripts as your notation. You should. I recommend it. Okay, can someone help me? What is zx in this case? Think of y as being a fixed number. You don't know what y is, but whatever it is, it's fixed. X is the variable, so I want to take the derivative with respect to that x. What do I get?
Would it be y squared times e to the xy?
That is correct. I'm trying to figure out who this is. Jonathan. I can tell by the process of elimination, you're the only one who has unmuted their Zoom account. So even if you don't want me to know who you are, I can tell. And Jonathan is correct. You guys see how he got that? He said y squared e to the xy. That's because when I take e to some exponential function like this, and I want to take the derivative of it, the xy will remain, but I also have to multiply it by the derivative of xy with respect to x, which is y, which is where that other y comes from. Let me do that in a few steps. You get this y, it's a constant, so I'm going to multiply it by the rest. I will leave that y. Then this e to the xy, I'm going to leave it because it's like the derivative of it is itself. Then I also have to multiply it by the derivative of the exponent xy, which in this case is y. Sorry, I should have left myself more space here. I'm going to erase this. Which I think Jonathan said he went one step and kind of cleared that up to say y squared e to the xy. That's correct. The partial derivative of z with respect to x is y squared times e to the xy. Do you guys have any questions about that? How we got that? No questions? How about z to zy? What will that one be? Now I can't just treat y as a fixed constant that's being multiplied by the function. It's a real variable there. I'll have to use the product rule, correct? The product rule, if you recall, is this u prime v plus v prime u, something like that. So what will it be? Let's do it. Should we do it together? Do kind of step by step. What is the partial derivative with respect to y? Let's say the first part is u, the second part is v. I'm going to do, let's say u prime v plus v prime u. Okay. U prime, I want the derivative of y, that's just 1, times v, I'm going to leave that one unchanged, e to the xy, plus, oh, wait a second. No, that's right. I should just leave it unchanged, e to the xy, correct? Now I'm going to take, leave the first term unchanged and take the derivative of the second term. And that would make it y, the first term unchanged. Now I want to take the derivative of e to the xy with respect to y. And just like before, it's like I'm leaving e to the xy there, but I'm also multiplying it by the derivative of xy because xy is the exponent for this. The chain rule here. I'm using the chain rule to say, what is the derivative of e to the xy with respect to y? It is e to the xy, but now times x. You guys see where this x comes from? This x comes from like the chain rule. It's like, oh wait, we're not done. We also need to take the derivative of what's inside there, that xy. And because we're taking it with respect to y, not x, it's an x. Okay, so let's see what we get. Does that look right? E to the xy plus xy e to the xy. If you wanted to, you could even make it simpler. Okay, and there's one more that I have as an example. That is the natural log of x plus 1 over x. Here we go. The natural log, this is what z is. So what is the x? Is there glare here? Is the glare making it worse? All right, so this is a natural log of a fraction, x plus 1 over xy. We could split up this natural log if we want. Won't change the answer. The answer will be the same no matter how we do it. You guys want to do that? What do you say? Split up the natural log or leave it?
Split it up.
Split it up. Let's do it. Okay, so this is equal to the natural log of x plus 1 minus the natural log of xy. This is a really handy school. So even not school, skill or tool. I mixed the word skill and tool and said school. My brain works that way sometimes, but I think the glare is bad. It's actually better without the glare. I turn off that light. So yeah, when you have the natural log of a fraction, it's equal to the natural log of the numerator minus the natural log of the denominator. Okay. Now it's probably even easier to take the derivative of this thing. The derivative of the natural log of x plus 1 with respect to x is simply 1 over x plus 1, correct? That's the important thing about natural logs and their derivatives. It's just 1 over whatever you're taking the natural log of times the chain rule factor if there is one, but there isn't one in this case. All right, and how about this next one with respect to x? 1 over xy. Now there is a chain rule factor because I have to not just take 1 over xy, I have to take the derivative of xy with respect to x, which is y. Right? This equals minus 1 over x. I think those two y's cancel out. You know, you could have convinced yourself that this wouldn't have a y in it. You know how? You could have gone even further and say this right here. I'm not sure if I should show you this, but it equals minus the natural log of x minus the natural log of y. So of course that y is going to disappear and you'll just have natural log of x and that becomes 1 over x. Okay. Didn't have to see that, but if you did, you could have easily convinced yourself that z of x wasn't going to have any y's in it, and it doesn't. Spoiler alert, for z of y, there will be some x's, I think. Actually, wait a second. Wrong spoiler alert. I take it back. For z of y, there will be no x's. I was thinking that you couldn't separate it, but actually you can. You can separate it exactly the same way. And probably the answer will just be negative 1 over y. Because this part won't have any y in it. This part won't have any y in it. The derivative of negative log y is negative 1 over y. Wrong spoiler. I think that's it. You guys see how I got that? If you didn't know the rules of logarithms, or I should say the properties of logarithms, and you had gone straight to this thing and tried to take the derivative of that, that would be okay. You would still get the right answer. Let's pretend you didn't know that. Let's pretend you didn't split it up like I think it was Jonathan said and just went right to this and tried to go at it. I would say the log of that thing is 1 over that thing, which is just to take the reciprocal to flip the top and the bottom and you would get xy over x plus 1. But you'd have to multiply it by the derivative of that thing with respect to y, which is, because y is constant, or y is the derivative, you just take the constant x plus 1 over x. What did I do wrong? Oh, it's 1 over y. I'm sorry. Yeah, 1 over y becomes negative 1 over y squared times whatever the constant factor is. So let's make sure we get that. Be negative 1 over y squared times the constant factor where, which is x plus 1 over x. You get this big thing here, cancel, 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 cancel. This y would cancel out with one of the squares. You get one of the y's, you get negative 1 over y. Yeah, you get the same answer. But the original question was find the partial derivatives of z, and we've done it. For x, it's 1 over x plus 1 minus 1 over x, and for y, it's negative 1 over y. I think that's the answer. And if you look at my slides, I also have the answers there. Current slide. Yeah. There they are. These are the ones with respect to x. These are the ones with respect to y. Same answers we got, I believe. Okay. You guys have any questions about that? I mean, I didn't give a really, really complicated one, but making it longer, it doesn't make it more conceptually difficult. It just makes it computationally difficult. You know, you have more steps for it. If you use the rules of differentiation properly, you'll get the right answer. And me adding more steps doesn't change, you know, the concept of partial derivative. It just changes the work involved. So let's talk about marginal utility here. If a consumer has a utility function, utility is a function of n consumption choices. I can choose how much of good 1 I want, how much of good 2, good 3, all the way up to good n. And x1 is a variable that says how many units of good 1 do I have, dot, 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 all the way up to xn, which is how many units of good n have I chosen. If I have a utility function which describes that, the marginal utility of good I is simply the partial derivative of u with respect to the variable xi, where I is any number between 1 and n. So if let's just do some examples here. If u equals xy, I'm sorry, u of x and y equals x times y, what's the marginal utility of x? You can just say that with words right now, I think. What do you guys think? In example 1, what's the marginal utility of x? You get my question? I'm hoping somebody is listening and will answer. The question is, if this right here is my utility function, oops, u of x and y equals x times y, utility that I get from having x units of good 1 and y units of good 2 is equal to x times y, then what is the marginal utility of x?
Y.
It's y. Thank you. 3 of you said it at the same time, and you're all correct. The answer is simply y. You take the partial derivative of this with respect to x, and you get y. All right, let's look at example 2. Now, you may recognize this as a Cobb-Douglas function. X to the alpha times y to the 1 minus alpha. How about in this case, what is the marginal utility of x in that case? It's actually something that happens a lot in economics. Functions that look like that, and it's nice to be able to be familiar with how to take the marginal utility of a function like that. What do you think it is? You have x to the alpha here, correct?
Would it be alpha times x to the alpha minus 1 times y, 1 minus alpha?
That's exactly right. You guys hopefully heard what he said. Alpha times x to the alpha minus 1 power times y to the 1 minus alpha. That's what the marginal utility of x would be. So this actually is a common utility function. You know, if you think of x as being food and y as being shelter, you can really express people's utility in functions that look like this, where alpha is some parameter. And the marginal utility of x is alpha times x to the alpha minus 1 times y to the 1 minus alpha. You're just using the rules of differentiation there to get that. I think I have the answers there. We got these answers correctly. Okay, now let's talk about the marginal rate of substitution. Those of you who've had economics classes, microeconomics classes, hopefully you know what this is. It's actually, well, so technically it's the rate at which a consumer would be willing to give up some of good I on the margin in order to receive some of good J. It's not like how many goods would you be willing to give up. It's the rate at which you'd be willing to give up good I for good J. So if it's 1, if the marginal rate of substitution is 1, that means I'm equally happy substituting good I for good J on the margin. If the marginal rate of substitution is 2, that means you got to give me twice as much of good I to get as I give up of. I'm sorry, you're giving up good I and getting good J. Okay, if it's 2, the rate, I'm actually willing to give up more I. J is more valuable to me in this case because I'm, I'll give up twice as much I if I can get J. And a marginal rate of substitution of 1/2 means actually I'm only willing to give up good I at half the rate at which I would need to get good J in order to make me just as well off. That's what the marginal rate of substitution is defined as. But there's a very interesting and helpful property of the marginal rate of substitution, which is that it's equal to the marginal utility of x divided by the marginal utility, I'm sorry, xi divided by the marginal utility of xj. You should think of I and j as like the index, the type of good you're talking about. Which good? Good I or good j. So the marginal utility of xi, how much of good I you have, divided by the marginal utility of xj, how much good j you have, that fraction is equal to the marginal rate of substitution, which is just a often heard and convenient. I don't know if convenient is the right word, but it's a property of utility functions and indifference curves, and this choice that a consumer has is largely determined by what's going on in the margin, in particular, what is that person's marginal rate of substitution. Okay, let's go on. That's just a definition of marginal rate of substitution. Here's some MRS problems. Oh, by the way, you've probably done this many times when there's only just 2 goods. If there's only 2 goods, you can think of this as like the slope of the indifference curve. So if you had a good microeconomics professor in the past, and they were willing to do some math and some calculus, maybe you may have seen this already as like, okay, yeah, that's just the slope of the indifference curve. It's actually negative, the slope of the indifference curve, but no big deal. Okay, that's not going to help you when you're doing a function of 3 variables. So that's kind of like, that's one of the points of this class, is to say, I want you, the student, to stop thinking of economics problems as just being graphs, just being stuff that you can graph and draw a line and say, well, there it is. It's that point on the graph. And why? Because that's how I was taught to do it. I was taught to find this point on the graph, and that's the answer. Well, I'm giving you problems now that are 3-dimensional. It's actually 4-dimensional here. X, Y, and Z are 3 dimensions, and utility is a 4th dimension. You can't even attempt to graph that. And I'm giving you a sort of a complicated utility function here too. It's the natural log of x times y plus 1 plus z squared. That's a utility function. The concept of marginal rate of substitution still applies here, even though you can't visualize it. I don't want you to visualize it. I want you to understand the math. And that is to say, okay, Let me read this problem. The problem says, find the marginal rate of substitution between good X and Y, given the consumption bundle 1, 2, 3. You can solve this. How? Find the marginal utility of X and divide it by the marginal utility of Y, evaluated at this point, 1, 2, 3. So you have to plug in. I hope you guys are okay with this notation here. This is a ordered triplet, 1, 2, 3. This means X equals 1, Y equals 2, Z equals 3. So like, instead of me writing that out, X equals 1, Y equals 2, Z equals 3, I just write this ordered triplet, and hopefully you know what that means. If you didn't know, I'm telling you now. And then so I'm asking you 2 practice problems here, but let's do this. What do you guys think? We did the pencil and paper before. Should we do annotation now? And you can compare which one's better. I'll do annotate now. The good thing about annotate is that you can still see this problem up on the screen while I write. So that's good too. All right, so what's the first thing I should do to, to solve this problem? I would say we should find the marginal utility of X. Excuse me. What should we, how should we do that? What's the marginal utility of X? Maybe I'll write it like this. Ux equals, what does it equal? Can anyone help me here?
Would it be 1 over X?
1 over X, and that's it? Yeah. Is this Jonathan again?
Yes.
I think Jonathan, you seem to be good at doing a bunch of steps in your head, right? Maybe I'm not sure how you got the answer, but maybe what you thought was, let's separate out the log X and log Y plus 1. Then the Y's are all separate, they disappear. The Z's are separate, they'll disappear. The only thing left is log X, and the derivative of log X is 1 over X. And you know what? He's right. You guys agree with that? And do you want me to show you how you get that? Or how about this? Please ask me for clarification if you don't understand how you get to this Ux equals 1 over X. But if nobody says anything, I'll just go on. I'm not saying you're bad for not saying anything. You might not want to. I'm just letting you know what my plan is. My plan is to go on. Uy. It's actually not that hard to get Uy, is it? What would it be? Anyone besides Jonathan want to give me an answer?
Is it 1 over Y plus 1?
Correct. Thank you. I bet you're Kai, aren't you?
Yes.
Sound like Kai. It's a doppelganger for Kai if you're not Kai. Let's go ahead and write UZ here. What's UZ?
2Z.
Correct. 2Z. All right. So we have calculated the partial derivatives with respect to X, Y, and Z. And that's all of them. That's all 3 of them. Okay. This question, find the marginal rate of substitution between good X and good Y, given the consumption bundle 1, 2, 3. Remember, this has an economic meaning. The meaning is, what's the rate at which I'd be willing to give up some of good X in order to get more good Y? We can calculate that using this math. And that is to say, I want to take Ux divided by Uy. Ux over, here's where we figure out if I have enough space to annotate on this PowerPoint slide. Ux over Uy is, well, it's going to be a fraction. The denominator is going to be X because that comes from Ux. But the numerator is going to be Y plus 1 because 1 over Y plus 1 is simply Y plus 1. And remember, the problem says to evaluate it at the bundle 1, 2, 3, X equals 1, Y equals 2, Z equals 3. I plug in 2 for Y there. I'm just going to go right to the answer. or not right to the answer, but I'll go here. 3 equals 1. I think the answer is 3. I'm willing to give up 3 units of x to get 1 unit of y on the margin. Okay? Is that right? Hmm.
Do you have to divide that by the UZ?
No, you don't do UZ.
Oh, it's just X and Y. Okay.
Yeah.
Professor, for the UZ, finding the marginal, or is it the marginal derivative? Is it 2x or is it 2z?
Oops. Gosh, I'm really glad you said that because that would have been here on the video forever. And in fact, it already was on the video for a long time. Thank you for telling me. Should have been 2z. Dang it. I can't go back in time and fix that mistake. Yeah, that should be the derivative of z squared with respect to z is, of course, 2z. Sorry. And the worst thing is that sometimes there will be an x in here. You know, this happens to be a problem where here there's only x's, here there's only y's, and here there's only z's. But I should just let you know, in general, that won't always be true. There could be x's or y's or z's in any 3 of these. Partial derivatives could have any 3 of the variables. This is maybe rather a simple function because it doesn't have that property. Each one's sort of isolated when you look at the derivatives. But let's do this second one here. For this one, oh, by the way, someone asked about z with respect to this problem here, this first problem. Let's call this problem 1 and call this problem 2. Problem 1 is only asking about good x and good y. Good z doesn't have anything to do with this. When you're talking about the margin rate of substitution, it's only margin utility of x over the margin utility of y. And it's okay that z is not in there. Now for problem 2, now it'll be margin utility of x over margin utility of z. That's the thing that's changed here. So it'll be ux over, I'm getting really low on the screen. I hope it doesn't get cut off. Ux over uz equals, well, ux is 1 over x, and uz, I'm actually writing it out here for some reason, divided by uz, well, that's like saying 1 over 2z, isn't it? And that was, oops, I did it again. I keep saying z and drawing an x. Maybe who knows if I said z before, but I definitely wrote x. Okay, we get this expression 1 over x divided by 2z, but I just prefer to write it this way. You can kind of easily see what's happening. Now I plug in x equals 1, z equals 3, and I think you get 1 over 2 times 3, which is 1/6. I think that's the answer. So the answer to question 1 was 3. The answer to question 2 was 1/6. I believe that's correct. Circle the answers. And once again, you use the concept of partial derivatives to get this, rather than trying to think about, okay, what's the slope of this function at this point, 1, 2, 3. Already you're thinking 3 and perhaps even 4-dimensionally, and just don't bother. The partial derivatives are good enough to give you the intuition of what's going on here. Any questions about this? This is an application of partial differentiation. It's calculating marginal rates of substitution. Calculating marginal rates of substitution can be done easily if you know how to take partial derivatives, which are written here. Of course, the more complicated your utility function, the more complicated these partial derivatives will be, but the same process will work.
should be okay. All right, next slide. By the way, this gives you the answers. So if you didn't want to wait and see what I wrote there with all of that annotation, this is exactly the same thing. Okay. Do I have time to do this? I've lost the ability to tell time once I use my phone and my computer for. That's embarrassing. It's 1:23. Okay, we have 20 minutes left. Production functions are very similar to utility functions, except now the inputs to the function aren't units of consumption, they are units of capital and labor, usually. But there's this concept, marginal rate of technical substitution of L and K. That's the same thing. I would take the partial derivative of L and divide it by the partial derivative of K. For example, in this problem here, the production function is Cobb-Douglas because it's K to the alpha, L to the beta. And if K equals to 1 and L equals 2, what's the marginal rate of not substitution, but technical substitution? Because this is a production function, that's why it's called technical substitution. You would just take this partial derivative with respect to L, that's this thing here on the top. The partial derivative with respect to K, that's this thing here on the bottom. There's a lot of simplification here, thankfully. K over alpha divided by K over alpha minus 1 just leaves you a K in the numerator. L to the beta minus 1 over L to the beta leaves you with an L in the denominator. You can plug in 1 for K, L is 2, and you get beta over 2 alpha. Okay. I'm not going to go over that one any more than that because I think it's very similar to the last stuff. I do want to talk about higher order partial derivatives. Because I talked about the second derivative of a function. And when you only have one variable in that function, it's pretty obvious what you mean. You take the derivative once, then you take the derivative again. That's the second derivative. However, it's a little more complicated when you have a function of multiple variables because you can only, the first step is, the first derivative is really just a series of partial derivatives. And now the second derivatives, what are they? Well, they're actually the partial derivative of the partial derivatives. And you can take, it matters which variables you're taking the differentiation with respect to, and you can write them this way. Best way for me to explain it is to give you an example here. Or let's now consider a function. I kind of like annotating. Annotating is generally fun. Let's take this f of xy. Notice it only has two variables in it. That means it's going to have exactly two partial derivatives, right? Fx and fy. Those are the two partial derivatives of f. If I asked, okay, how many second order partial derivatives of f are there going to be? You may pretty easily find out yourself, if you thought about it, that the answer is 4. There's going to be 4 second order partial derivatives of f, because each of these two first order derivatives, partial derivatives, are themselves going to have 2 partial derivatives. And it might make sense to remind you here that fx here could be a function of x and y. Fy could be a function of x and y. So it's meaningful to think, okay, what's the partial derivative of x with respect to, partial derivative with respect to x of fx? It's something you might call fxx. But you also get fxy. And then this one will give you the 2 there, fyx and y, y. You see how you actually get 4 second order partial derivatives from this one function f. There's one function, there's 2 first order partial derivatives, and there's 4 second order partial derivatives. This just comes from the fact that when you're taking a derivative, you got to say, okay, with respect to what? And there's more and more things to answer with respect to what as you get lower. Like, for example, this is a second order derivative with respect to what? Well, first with respect to x, and then again with respect to x. What about this one? Oh, that's the derivative first with respect to x, then with respect to y. And then this one is pretty similar, except y and x are in the reverse order. And then this is the last one. Let's skip down to here. Young's theorem, it says that fxy is always equal to fyx. Oops. So these two here are always going to be the same. That's actually kind of a neat shortcut because it means you don't have to calculate them twice. Calculating it once is good enough because it'll always be the same. It's an interesting feature of functions that you might try to come up with some counterexamples like, wait, what if x is like really crazy and y is really normal? You take the derivative with respect to x and then you go to y, and doesn't it matter what order you do the differentiation in? No, it doesn't. I challenge you to come up with a counterexample to Young's theorem where it matters in which order you take the partial derivatives. You won't find it. If you do find one, it means you made a mistake in your differentiation. Okay, or the derivatives, they weren't actually differentiable functions. I should say that too. You can only do this if the functions are twice differentiable. Okay, you can't even find what these things are. I'm sorry, this is, the more colors I add, the more it just looks like a third grader's doing artwork, and it looks like a horrible, awful mess. I'm going to clear my drawings now. Okay, so what I have left on the screen is just a description of what higher order partial derivatives are. And these are all just kind of fancy ways to writing it. What I've written here, the left or the middle, those are the fancier ways to writing it. But in this class, I'm fine with you just thinking of it using the subscripts. The subscript way of writing it is the most efficient, the most compact way to write it. And I, as the instructor, will always be able to tell what you're saying if you use that notation, which is important. Okay, you guys have any questions about what a higher order partial derivative is? Okay, next slide. The Hessian matrix is important. And in fact, it's one of the main reasons I spent all that time talking about matrices. It's not the only reason, but it is nice that I can talk about matrices now since you know what a matrix is and we spent some time on them. The Hessian matrix is, by definition, a matrix of second order partial derivatives of a function. In fact, it's all of the second order partial derivatives of a function. So if you have any function that has n variables, n input variables, in this class, generally, we'll talk about n equals 2 or n equals 3, and that's it. Either n equals 2 or n equals 3. But here, let's just say in general, for whatever n is, you can speak of the Hessian matrix as the matrix where the first row of the matrix are all the second order partial derivatives of the function, where the first variable is x1, which is the first input variable, is the first, the derivative is taken with respect to that very first variable, and then all of the rest of them complete the rest of the first row. So it'd be like fx1, x1, fx1, x2, ... x1, xn. It goes, this first row all has x1 first. The second row all has x2 first. All the way down to this row all has xn first. When I say first, I mean taking the derivative of first. Of course, you could look at me and say, well, you just told me that because of something called Young's theorem, that it doesn't matter which order you do the derivatives, and that's right. What does that tell you about this matrix? Can we say something about whether H is symmetric? Do you remember the word symmetric? A function, I'm sorry, a matrix is symmetric if it's equal to its transpose, meaning that, I just love to annotate. I'm going to annotate more. Apologize, everybody. You know, H prime or HT. Do I use T? I think I use T in this class. HT for H transpose is going to be the same thing, but with, you know, flipped. The rows become the columns and the columns become the rows. They're going to be equal to each other. They're not equal by definition because, you know, the way that they're written is different, but they're equal because of Young's theorem, which says that anytime I take the partial derivative, the second order partial derivative of a function, it doesn't matter the order in which I take the differentiation. So, you know, there's going to be an f x1, x2 up here, and these two values have to be the same, which means H is symmetric because it's equal to its transpose. If I had done it here, this one would be the same, x1, x1, but this one here would be f x2, x1. And then down here, I'd have this f. This is more complicated than it needs to be. I'm only trying to make the point that H is symmetric. Okay. You might ask, who cares about the Hessian matrix? It seems like a lot of notation and dots for no particular reason. Well, how dare you say that? I'm just kidding. The Hessian matrix reveals a lot about what's happening for a function, not in the sort of first order slope way. It's not really that. It's more about like saying what's happening with the curvature of a function. Just like if I gave you, you know, if I say f of x is a function, and then you thought about, okay, what's f prime of x? Okay, f prime of x is like the slope of that function f. And then you said, okay, what's f double prime of x? F double prime of x is, it's like the curvature of the function. It says whether it's convex or concave, right? That's what f double prime is. For now, I'm thinking of a function of just one variable, and you have this intuition. It makes sense to you. Well, for these complicated ones, you know, you have. I'll just do a function of two variables now. F of x and y, that's the function. You don't have just one derivative. You have these two partial derivatives, fx and fy. And what that's telling you about f is, okay, like marginal utilities or marginal products, it's telling you how the function changes just when you look at one variable and not the other. One's fixed and the other's changing. It's kind of like slope. It's kind of like what's happening on the margin of f. And now for the second derivatives, you have this h. H is like the equivalent here. I don't know why I think of it this way, right? Where here's a chart where we're talking about the function, the first derivative, and the second derivative, and now I'm teaching you about this thing here, h. It kind of satisfies the same thing that f double prime does, which is to let us know in a sort of second order way what's happening with this function. And when we get to maximization problems and minimization problems, it will satisfy the same thing there too, where this tells you about, this tells you about the first order conditions for maximization or minimization. This tells you about the second order conditions for maximization and minimization. So we'll learn about the Hessian, we'll learn about its properties, and how it, you want to say something about, is a point a maximum, a local maximum of a function f? You'll talk about the first order conditions to say, is it a maximum? Well, it has to satisfy the same first order conditions, f of x equals 0, f of y equals 0. Those are the first order conditions. But then when we get to the second order conditions, like for maximum, it was this is 0, and then this had to be, is it positive or negative here? F double prime has to be positive or negative? It has to be negative, right? For a maximum, had to be negative. F double prime of x should be negative if we're looking at the second order conditions for maximization. Hope you remember that. We did that a couple weeks ago. So now we have H. You can't just say H less than 0. What does that even mean? You can't say a matrix is less than 0. We will have a corresponding condition to say about H. And I'll just tell you now, it should be negative definite. If it's negative definite, that will be our equivalent second order condition for maximization. Of course, I haven't told you what that is, and you shouldn't expect that on the quiz. Definite. I'm not good at writing with the mouse. Actually, that wasn't that bad. You can't complain too much about that writing. All right, so all this that I've scribbled on the screen now is in order to try to convince you that actually the Hessians do matter for this class. I'm not teaching them to you for no reason. We'll talk about a maximization problem or a minimization problem, and you get to the point where in order to really know if you found the maximum or the minimum, you should look at the Hessian and try to figure out if it's negative definite or positive definite. And that will be equivalent to the second order conditions that we've had already for the stuff we've already done. What time is it? It's 1:40. I have 5 more minutes. You guys have any questions about the Hessian? Oh gosh, I've never actually had us make a Hessian yet. Can we do that right now? Let's construct a Hessian matrix. Here we go. No, I've lost the ability to do anything. Zoom meeting, share. Yeah, let's go back to my slides. I'm going to go back to my slides. Oh, shoot. Here we go. From current slide. Let's do this. Somebody have a chat? What topic should we focus on for the quiz? Yeah, we'll talk about partial derivatives and the Hessian matrix and homogeneous functions. How's that? Is it Amina that asked that? Yes. Okay. So this could be on the quiz. Let's do an example of it. Find the Hessian matrix for this function. What should I do? I should, well, first of all, know there's 2 variables here. So H is the Hessian matrix. It's going to look like a 2 by 2 matrix, right? 2 rows and 2 columns. I'm going to write it here. Hessian matrix. So this is something I could ask, although how would I ask you this on a Blackboard multiple choice quiz? I don't even know. I may ask you to do a quiz where you write on a piece of paper and then scan or take a picture somehow, because this quiz is going to have a lot of math on it. That's hard to make it multiple choice. Let's do this now. What belongs in the upper left corner of this Hessian matrix? It is the partial derivative of x, partial derivative of the partial derivative with respect to x, both times. So let's think about that. What is f of x of this function? 2x squared y. Then I'm going to change this x squared will become a 2x. The 2 will still be there. We'll get 4xy, right? Agreed? What about f of y? It's going to be, this will become 2x squared. And this one will be plus 6y. What I've done so far is just take the partial derivative of f with respect to x and the partial derivative of f with respect to y. This will help me fill out the Hessian matrix, because the Hessian matrix is actually the partial derivatives of these guys. What belongs in the upper left is the partial derivative of this with respect to x. You guys see what it's going to be? It's just going to be 4y. 4y. What belongs in the top right is the partial derivative of this with respect to y, which is 4x. What's wrong there? Did I do this right? I think so. What goes here is the partial derivative of y with respect to x, which is once again 4x. Oh, that's good. It better be. Remember, I said that was all this and this were always the same. So you see how I got this? This is fxx, fxy, fyx. What goes here is the partial derivative of y, and once again, with respect to y, what would it be? 6. I think that's the answer. Find the Hessian matrix for fxy equals 2x squared y plus 3y squared. The answer is the 2 by 2 matrix, 4y, 4x, 4x, 6. Do you guys see how we get that? I didn't write it over here, but like fxx equals 4y, I got that from this. fxy equals 4x. Of course, fyx is the same. fyy equals 6. I get that from there. Do you guys have any questions over how I got this? Let me take my phone away. I'm running out of time. Let's do the quiz at the end of class also. Okay. So maybe we'll have some time during class to talk about this stuff or a little bit of new stuff, but I'll make the quiz only over the stuff that we've done up until now. And that includes partial differentiation and the Hessian matrix, which is the second order derivatives of a function. And we talked about marginal rates of substitution as well. So I could ask you something about that on the quiz. I could ask you about what it means for a function to be homogeneous and the degree of homogeneity. So here's a function. Is it homogeneous? If so, what degree? I can ask you questions about that. That's actually an easy question to ask as multiple choice. The Hessian matrix will be harder. So still trying to figure out a way to make a quiz where I ask you about the Hessian matrix. But I'll try to do it. Why does it say John's phone? I thought I turned off my phone. Okay. Can I answer any other questions for you guys about the quiz, about the rest of the class going forward? What do you think? How do you feel? You okay? You okay with partial derivatives and the Hessian matrix? Remember, the Hessian matrix is not just the partial derivatives, it's the second order partial derivatives. So it's takes a little more time to make it. And we'll have our quiz, how about at the end of class on Thursday? So you have some time during class. Yeah. If like between then and now you think of something like, wait, I still want to ask you about this, you could ask me about it in class on Thursday. Okay,